So here we are with a 1.0 molar potassium fluoride solution, and by solution, let's remember, that means it's dissolved in water. So we want to write down accurately what the reactants are, because the question is asking what reaction will take place at the cathode, which we know that's going to have to be reduction, and at the anode, and this one is our oxidation. So let's decide what are the reactants that we have in this solution. We've got potassium and fluoride, but they don't exist as a molecule. This is an ionic compound, and it's a very strong electrolyte. Remember, potassium is an alkali metal, so in our solubility rules, it's in the same group as Na. All right, so anyway, the alkali metal group is always soluble. Does anybody want to hang out with this guy? Nah, so we got to write him all by himself. And to form this ion, we need to show this reaction. This will be our half reaction. And if you're not sure what to write for potassium, you just look at your reduction table and see what does that reaction look like. So let's go there. I opened the reduction table. Here it is. The potassium reaction will probably be down towards the bottom. There it is, I see it. Boy, way down towards the bottom. So, where did my clicker thing go? Here it is. Let me just highlight that for us. This reaction where we're adding an electron to the potassium ion to form potassium, the element, in atomic form, that would be a negative 2.92 volts. And that's the value we were looking for, so let's write that into our slide. Negative 2.92 volts. This is an important part of how we decide what is the reduction and what is the oxidation. So we're looking for the most positive value. Let's continue on then. In addition to potassium, we'll have fluoride ions. And those fluoride ions come from the atom fluorine that we've added electrons to. And since fluorine is diatomic, then we make 2 ions for every molecule of fluorine. All right, back to the reduction table so that we can find the value for fluorine. And that's probably near the top. So let's write on up here and find fluorine. Oh wow, it's the very top of the top. Now if you'll notice here, I know what we'll do. There, now we can see it. Notice that this reaction is written with the fluorine on the left-hand side and the fluoride ion on the right-hand side. And since that's opposite of the way we've written it, we're going to change the sign of the voltage. Why would we write it that way? You see, since potassium ions and fluoride ions are the actual reactants in this solution, then we've got to write it that way. Now I forget what it was. 2.83? Does that sound right? I didn't write down my answers. Well, I did write down my answers, and I left them in my classroom. 2.87. All right. Sorry about that. 2.87. Let me get that eraser. And back to again, 2.87 volts. Okay, well that's not the only thing in our solution. We've also got this nonsense, water. And water doesn't exist purely in molecular form. By the pH of water, we know that some of it's going to dissociate. And especially if we have an electrical current through there, then we're going to get some of these waters decomposing into 2 different substances, hydrogen and oxygen. So now we're going to have to figure out what these reactions are. We worked through the half reactions in class. You're welcome to go through all of that and, add water to balance the oxygen, the hydrogen ions, and all that good stuff. But you know what? There's a shortcut. Here it is. Look on the reduction table and find that reaction. So let's find it. It has water in it. the one that's making hydrogen gas. And this is one of the ones that we want. So this reaction's already balanced for you. That's the beauty of this reduction table. You're going to get to use this on your AP Chemistry exam. And don't forget, you don't have to do all the half reactions. In fact, all of these are the half reactions that you'll have to do for the net ionic equations on question number 4. And they're already done for you. If you have a redox reaction, look on here to make sure that you are getting your charges right. The hard part for you is going to be deciding when you have two different charges, which one to use, like this chromium or this chromium. And there's probably another chromium somewhere on this table, and you have to decide which is the best one in that situation. Give it a shot. All right then. So we had 2 waters makes hydrogen and 2 hydroxides. And we had 2 electrons somewhere or other, and I suspect they belong over here. Since this hydrogen is in its plus form, and this hydrogen is in its 0 form, I bet we put our 2 electrons on this side. And that was a negative 0.83 volts. So now let's go get that reaction for oxygen, where we have water on one side and oxygen on the other. That's going to come in handy for the next part of the reaction. So scroll down to find the one with water and oxygen. Our reaction has water on the left-hand side. So we're flipping again. When we flip a reaction over, that changes its potential to negative. So you have to change the sign. Because I want my water on the left-hand side, since that's what's in our beaker, right? So we better write a reaction that accurately describes what we have. Alright, so now that we've described all of the reactants that we have in the solution, we're going to have to decide which of these reactions is most likely. They're all possible reactions, and so we call these competing reactions. So we have to decide which is our best choice. Yeah, you get it. Competing, blah, blah, blah. I don't know if that's going to show up or not. Okay. So, for reduction, remember, is the gain of electrons. Let's figure out which 2 reactions show the gain of electrons. And it would be right here, where we're adding an electron to potassium ions, and right here, where we're adding the electron to the water. So which of these 2 reduction reactions is most likely? Well, the one with the more positive value is going to be the winner. And a negative 0.83 is more positive than a negative 2.92 volts. So our winner here for the reduction reaction at the cathode is the water reaction. So at the cathode, this is the reaction that's going to take place. Right here. Okay, so now we've got to figure out what's the best choice for, I'm going to have polka dots or stripes or whatever. We got to figure out what's the best oxidation reaction. So where the electron's being removed, we're going to decide which of these 2 is a better predictor of what's likely to happen in this oxidation reaction. So we're looking at these 2 reactions, the fluoride and the oxygen. We're again looking for the more positive of the 2 values. So comparing negative 2.87 to negative 1.23 volts, this is our reaction that is more likely because it is the more positive of the 2 reactions. So at the anode, our best reaction, the most likely reaction, is going to be the one with the more positive reduction value, and it's this reaction right here. So truthfully, in this description, the potassium fluoride isn't doing anything at all. And that seems pretty familiar to us. That potassium and fluorine would be spectators seems to make a lot of sense, since nobody wants to hang out with that guy. And the water is the reaction that we see, the hydrolysis or electrolysis. So we're splitting the water into hydrogen ions and oxygen ions. Hydrogen gas and oxygen gas. Wow. So when we add these two reactions together, of course, we'd be careful to balance, make sure it all works out perfectly well. But what you'll see in this reaction is a test tube at this electrode where oxygen gas bubbles up to the top of this test tube. And then in the other half cell, you'll see a test tube where hydrogen gas is bubbling up at the end of that platinum electrode. And so we'll get twice as much hydrogen gas collected, twice the volume, as we do oxygen gas because of our stoichiometry right here. Twice as much hydrogens as oxygens. Now, of course, if this was our galvanic cell, of course, we've got our half cells and our salt bridge and a wire connecting our two electrodes. It's usually a platinum wire that hangs down below so that we can get a place for that oxidation and reduction to occur. And naturally, we'll have a voltmeter there that's going to measure cathode minus anode, 0.83 volts minus a negative 1.23 volts, and we'll have it. All right, then let's do another one of those because I think it's good practice, and this is a very common multiple choice question on your AP exam, so I want to make sure that you get it. I want to know that you can do this, and I'm sure you'd like to know that you can do this too. Let's see. Here's my arrows that I like to have. Here's the whole answer, all typed up, all fancy. And for the copper chloride, since we're in solution again, I'm going to go ahead and copy down that water because it's in solution, right? That means we've dissolved copper chloride in water. And so consider your solubility rules here again. The chloride solution, the chloride rules is that anything is soluble except for silver, mercury, and lead. And since we're dealing here with copper, we know this is going to be completely soluble. It will dissociate into copper ions and chloride ions. In this case, we're going to get the copper 2 ion because we have copper 2 chloride. So what does this mean? On your reduction table, this is the reaction you'll find. We're going all the way to elemental copper. We have no indication that we should go to anything different, so we better go all the way to elemental copper. We'll look that one up here in a second. And we'll do the same for chloride ions. We've got chloride ions in solution, and how do we make those guys? We're going to start with chlorine. And since chlorine is diatomic, we better add 2 electrons, which will form 2 anions. And now let's go to that reduction table and compare our values. Chlorine reaction is right here at the top. Not the very top, but you know, top enough. It's a 1.36 volts. For the reverse reaction, it will need to be negative 1.36 volts. And I lost my writing, there it is. So negative 1.36 volts for this chlorine reaction. And now let's look at our copper. Oh, I wrote that in the wrong place. Sorry about that. 1.36 volts for chloride. And copper, we're going to have to go back and find that one. Got these 3 choices here for copper. Which one do we want? We want the one that looks most like ours, and that would be this one in the middle, where we have a 0.34 volts. We're not flipping this one, so keep that sign the way it is. So we have, whoops, wrong pen color, 0.34 volts. Hope you can read that, folks. Let's decide which is the better reaction. We have a couple of options. Here's a reduction reaction, and this one is also reduction because we know that when you gain electrons, that means reduction. So we're comparing these two to see which is more positive, and this is an easy choice. One negative value, one positive value. We have a clear winner. And now we're going to compare for the oxidation reaction. The loss of electrons is oxidation. So this reaction's losing electrons, and so is this one. Which is the more positive? This is a lot closer battle between these two, but this number is more positive. The negative 1.23 volts is more positive and negative 1.36 volts. So in this particular cell, we'll have the reduction of copper at the cathode and the oxidation of water at the anode. Well, there you go. That's how we do those problems. That's likely to show up in a multiple choice question or in a part of some other question about electrochemistry or something else. You never know where they might throw that one in for us.